Good morning, guten Morgen, guten Morgen, bien le bonjour, salam alaikum. This is a great pleasure to have you all here today for this very special session, the youngest session of all COP28. We have also the great pleasure to thank the Ministry of Environment from Luxembourg, who made this possible by its generous support. We have today a panelist, several panelists. Most of them were high school students when they did some environmental research back in Luxembourg. Now, most of them are studying abroad. They will explain what they did, what they achieved. They're eager to do that in a minute. But before that, I would like to call to the stage the director of the Foundation Young Scientist Luxembourg, Fondation Jeunes Scientifiques Luxembourg, who's organizing annually a contest for young scientists through which our panelists were actually selected. I have the great pleasure to call to the stage my dear colleague Susanna Young, Director of the Foundation Young Scientist. A round of applause. Thank you very much.
Good morning, Moyen. So I will also join Guillaume in thanking the Ministry of Environment to make this experience possible at the COP28, and also to give us the opportunity to present our foundation and especially our young scientists. So for this presentation, I would start with a bit of history. So the very first national competition in Luxembourg was organized by the Luxembourger Votes on November 1971. There is some mistakes due to the conversion of the presentation, but so for more over than 15 years now. And this is from this initiative that the association Jeunes Scientifiques was created in September 1977 to ensure the financial aspect of its competition. This association became a public utility foundation in 1992, and ever since we are supported by many supporters, so many supporters, except Luxembourg Votes, actually. So the article of the foundation states that our mission is the promotion of science among young people aged between 11 and 21 on national but also international level, and also in an extracurricular way. So that leads to the next point of our non-formal science education methodology that can be linked to the Kolb model. So a few words about the Kolb model. So it comes from David Allen Kolb, who is an American educational theorist whose interest is focused on experiential learning. And this experiential learning emphasized with 4 cycles, so concrete experience, reflective observation, abstract conceptualization, and active experimentation. I'm sure you already heard about this learning by doing quotation. So this is precisely illustrated our method of learning process for our young scientists. And not to mention that a lot of studies show that learning we are more likely to learn when being active than when receiving information passively. So with all this in mind, how the foundation design engaging science activities. So you already heard about the competitions. So the National Young Forscher Contest invites young science enthusiasts to present scientific projects made extracurricularly and presented in front of jury members composed of various experts from various fields. So here are some numbers. You can see that for the 5 past years, the participation is clearly increasing. Another thing that needs to be mentioned with the core model is we are strongly recommend to our youngsters to create their projects on auto-directed work. What does that mean? That means that you are completely free to choose your domain of predilection, the way you want to create it, if you need a tutor or mentoring, if you want to do it alone or with friends, it's totally free. And here we can see that this is extremely interesting how our youngsters is interesting on actuality. So on 2023, for example, the focus was more on environment. So this is really something that we can see when we let our youngsters choose their own domain of scientific projects. So then after the competition, they will have the opportunity, the reward is the opportunity to bring their project internationally. So depending on the level of the project, the age, the language speaking, our youngster will compete at the world largest competition as ISEF, CASTIC in China, GISF in Taiwan, but also attend the largest expo sciences worldwide and also attend the COP28. Then the second very important platform is the Luxembourg International Science Expo. So the idea behind this platform is to create a young scientist community and also to let our young Forscher that they are part of a big community. So this is a little bit the other way around. We are not sending our young Forscher internationally, but instead inviting the international laureate to come in Luxembourg for a week of science and cultural exchange. So a little bit about numbers as well. So here we can see that the interest was more focused on IT data and also biology medicine. And just to have a glimpse of the participating countries, on 2023 we received 16 different countries. So the last program, the last platform of the Fondation Jeunes Scientifiques called Science Next. So Science Next is a program that we are performing throughout the school year. The idea is to support our youngsters with methodology. The idea is to provide with coaching, workshops, conferences, lectures to help them in the process of developing a scientific project. So for that purpose, we are gathered a group of experts from various fields. So if our youngster needs to have support, for example, they have an idea but they don't know how to go further with it, how to well research on a certain information or topics, for example, how to well articulate an hypothesis. All of these steps within the process of developing a scientific project is really important, and we think that it is really important to not let our youngsters alone in this process. So, of course, Science Next is a platform to support our young scientists in this process, so to be well prepared for the competitions, nationally but also internationally. But above all, is also a platform that prepared our next generation of scientists to be to have the tools of critical thinking, for example, the tools to be analyzes, to be ready for studies at university, but also on the career journey. Voila. This is for the last platform of the young scientist. So just to sum it up, the Fondation Jeunes Scientifiques promotes science among young people between 11 and 21 on national and international level. For that purpose, we are organizing several platforms in a non-educational way, extracurricular way. So we aim to well equip the next generation of scientists that we have the chance to see now, to discover their project. So thank you for listening.
Thank you very much, Susanna. As you notice, we have some competition, noise competition with our neighbors, so please make as much noise as you can anytime you applaud. It's part of the game we're playing, right? Hi, Thomas. Good morning, Rafael. So now, it is my great pleasure to turn to the youngest young scientist of our delegation, Bartolomiej Novak. Please, round of applause for Bartolomiej. We divided this session into three main topics. First of all, our biggest problem, as you all know, CO2 emissions, responsible mainly for the main reason for global warming. Bartolomiej is a theorist. He's the only one in that category, and he will present what he's done in a minute. After that, we will turn to alternative, cleaner energy production solutions. And finally, we'll say a few words about citizen sciences projects. Bartolomiej, correct me if I'm wrong, you are only 17, right? You're a theorist, you're a musician, you're a composer, but you also write codes, and that's what you'll tell about. The floor is yours.
So, welcome everyone. I'm Bartłomiej Nowak, as was already mentioned, and I'm a student at the European School of Luxembourg in Kirchberg. And I would like to present to you my project about predicting carbon dioxide emissions using machine learning, showcasing both the technology behind it, as well as the real-world applications of this technology, especially in the context of climate change on COP28. So, the first question I would like to answer is actually why. So why should we use AI for global warming, for climate change? Many of you may just think that AI is something we use to generate some images, some text, doing your homework, and things like that. But it's something much deeper and much more diverse. For example, the Dubai Metro, which I think many of us use to get to the COP, is actually fully autonomous. It's AI-driven. And this just showcases this deep diversity in AI. And climate change is no exception. Climate change can in some ways be described with data. So here, in this case, we can also use AI to in some ways analyze global warming. And it's also important because, as you probably know, global warming is incredibly complex with many different factors affecting it, many different metrics possibly distorting our view of what is important, what is a bit less so. And in this case, AI is actually incredibly powerful because it can easily, it can understand patterns which humans struggle to find themselves and go through, and this huge quantity of data would just be impossible for a human team or purely human team, especially if you consider smaller countries like Luxembourg. We don't have the resources to have a 1,000-man team just go through all of the data we collect. So now that we have a common understanding of actually why we should use it, let's see how it's actually done. Every AI model starts with data. Anything you do, ChatGPT, the Dubai Metro. But of course, in every scenario, the data itself is a bit different. It has to be relevant to the topic on hand, to the problem you want to solve. In this case, I focus predominantly on economic data. So for example, global GDP, global oil production, coal production, also a bit more demographic data, social data like global population and driving distance. All of this data can be freely collected on the internet, which is actually one of the key limiting factors in any AI project development. And I understand that the discussion whether to make the data public and use it for AI use cases is a discussion all of its own, so I will not go deeply into that. However, no matter what data we collect, at first it is not actually useful for an AI implementation, for an AI model. Firstly, it has to be cleaned, so we just remove the unnecessary information, because there is kind of a saying in the machine learning community, garbage in, garbage out. So of course we want to avoid this phenomenon. And we just want to keep the information that is necessary and that is relevant to the problem we want to solve. And nothing less, nothing more. Secondly, in the second stage of data processing that is called, we have to normalize all of the values. So basically keep them into a range of 0 to 1. And this is basically because of the specific workings of the algorithms that really like to keep the data in this small range. Because for an AI algorithm, it doesn't actually matter the specific value of 4 billion, for example, in the case of population. It just needs to keep the relationships between the values the same and constant. We have all of the data, it's clean, it's processed, but just with data, nothing will happen, nothing will be analyzed. It is pretty useless by its own. For this, we need some algorithms. So in this case, it's called a deep neural network. This structure is made from things called neurons, which are basically things which take some input, like our economic data, and output some certain value. So in this case, it's the carbon dioxide emissions. This transition from input to output is determined by some values called biases and weights. And these are the trainable parameters which will be tweaked to actually get the output we need. So just to see some simple example, and the green nodes are the inputs, the bias is the red node, the weights, linking them are the weights, and the blue node is the output. And I would just like to mention one of the key advantages of these neural networks is the scalability. Because one neuron is actually pretty useless on its own. It can possibly solve very simple problems, but that we can do on our own. We don't need any help. But when you actually scale them, so you combine neurons, make millions, billions of them, then you can achieve some incredible results. And just to give one example, which everyone knows, ChatGPT has 175 billion neurons, 175 billion parameters to change. And this shows that when you just scale them up, you can achieve some incredible results. And in this project, it was no different. However, no matter how large the network is, no matter how complex, what data you have, at the beginning, you just get random values, which have no meaning whatsoever. So we have to train it. But how do we do that? Basically, we want to minimize a value called loss. And loss measures kind of a distance between what we achieved, so what the output of our network, and what is desired, so the real observed value. And basically, by actually minimizing the loss value at each training step, we get these values closer together, and we make a more accurate, better model. So, one example, output 37, these are output 40, and according to one method of calculating loss, because there are many different ways, many diverse for different problems, we get a loss of 9. And naturally, the model will try to get it to 8, 7, 6, ultimately to 0 in a perfect situation. And just to visualize it, this would be the graph of the loss values, smoothly going from some x value to 0. In this ideal world, of course, during real-world training, it doesn't happen too often, but just to simplify the problem. So, we've tried the model. Now we have to test it, which is probably the most interesting part. And thankfully, I can say that the model performed really well. We can see that all of the values, so the green and red curves, are incredibly aligned, meaning that the model understood the patterns well. It understood what affects carbon emissions in an accurate way. And it proves that, yeah, the pattern detection of neural networks is real and is capable of being implemented in problems like climate change. I would also like to mention one use case for making policies, for example, and understanding some changes in the world, because the previous case was the past. So what happened? But of course, as policymakers, we want to know what will happen in the future with the actions we make. Here I present 4 different scenarios indicating changes in the metrics I've used. So in this case, it's global coal and oil production. The red and blue curves represent a situation where we have an increase in coal and oil production. But I think more importantly, I would like to see the curves, with the yellow and green curves, which represent what happens with a decrease in coal and oil production. Especially the green one is interesting, which shows a phasing out of coal production and its effects. I mean, with this model, we can see that actually coal should be in many ways the priority of policymakers, because it has one of the main impacts on carbon dioxide emissions. So, to conclude, we see the accurate predictions of a machine learning trained model in predicting carbon dioxide emissions. We can see that it may have potential use cases in guiding policies and understanding how they affect future emissions, and in some ways quantifying the results. And just one more verdict I would like to make is, I think coal is probably one of the priorities in our fight against global warming. And I think I just want to show that when used properly, AI can be a powerful tool, and it can be a tool for a good cause. And it's not just doing your homework and writing some documents and images. Thank you.
Thank you very much, Novak. Now, we've talked about the gas of the devil, CO2. We will turn to cleaner energy production methods. One that is still producing CO2, but less than the other ones, biodiesel. David, please come to the stage. Round of applause for David, ladies and gentlemen. So, contrary to Bartek, David is not a theorist, he's an experimentalist. He spent weeks in labs to prepare this project, both at International School Luxembourg, but also at the University of Luxembourg afterwards. He will say more about biodiesel. Just quick note, David is a brilliant student. He's now attending lectures at King's College, London. And he will probably major in biology later, is that correct? Biochemistry. There you go.
Hello, everyone. My name's David Dalzotti, and I'm a student, first-year student at King's College London studying biochemistry, and I'm going to be presenting my project on biodiesels. So, what are biodiesels? There's some common misconceptions with biodiesels that I want to highlight, first of all. So, people think of biodiesels as this completely clean fuel that doesn't produce CO2 at all, and that is somehow related to biology because of the word bio in it. But I would like to clarify that biodiesels, it's essentially an alternative diesel fuel, and there are some key differences between the two. The main one is it produces less CO2, so it still produces some CO2, but it's less than diesel, and it's also made from fats. So it ranges from saturated fats like animal fats, all the way to unsaturated fats like vegetable oils and those things. So yeah, it still produces CO2, but it's better. And I would also like to add that it can be used in diesel engines, of course. There's no problem with it. It's exactly like diesel, except it has some benefits. So why are biodiesels better than regular fuels? So first of all, they are clean burning. So they, again, produce less CO2, and they also produce less soot and carbon monoxide. So it pollutes the environment less, and this is extremely helpful in cities where there's a lot of big population and a lot of pollution. Secondly, it is renewable. So of course, there's no problem of scarcity like diesel fuels and other petroleum fuels. It can be there's a lot of quantity, and it's renewable. And this leads me to the next point. It increases energy security. So because of its renewability, the prices of biodiesel won't change as drastically as diesel or other petroleum fuels. And this is extremely helpful in economies where we want commodities to stay at a certain price because we don't want to change the economy drastically. And lastly, the point that I looked into is that they can be made from food waste. So it brings a concept of a circular economy where whatever goes to waste goes back into use. And I would like to give you some statistics on food waste. So there's one third of all of the food produced in the world goes to waste. So that's roughly 1.3 billion tons. So it's a lot. And this for sure could supply the world with enough biodiesel. So let's go into the chemistry of it a bit. So it looks quite complicated, but trust me, it's a straightforward reaction. It's one reaction. Imagine in pharmacology or in medicinal chemistry where they have 20 reactions and they go from liters of reactants to milligrams of products. So here we really have one simple reaction. It's called a transesterification reaction. And so I would like to say one clear thing. So triglycerides are basically the fat molecule in saturated fats and unsaturated fats. And it's the fatty acid itself that changes, and this, then changes the fat into a saturated fat or unsaturated fat. And I would like to say that, so if you have 100 kilograms, for example, of triglyceride, you will get exactly 100 kilograms of fatty acid methyl esters, which are biodiesels. So it's really a proportional reaction, and it's quite efficient because we can produce a lot of biodiesel from it. So let's look into the details of the reaction. So transesterification reaction, essentially what's happening is the ester bonds in the triglyceride are switched and replaced. So basically, as you can see, the blue boxes, the fatty acids inside the triglycerides form the methyl esters. They're called fatty acid methyl esters, which are essentially the biodiesels. And the glycerol backbone of the fat forms glycerol or glycerine. It's the same thing. It's the same term, and this is a byproduct of the reaction, which can be used for example, soap manufacturing or other industries. So nothing really goes to waste here. So my research, the first part of my research involves looking at pure oils. So I wanted to first see the combustion enthalpy of the different biodiesels made from pure oils. So I would like to first explain combustion enthalpy is essentially the energy that is released when the biodiesel is combusted, under combustion. And the 5 oils I looked at were olive oil, sesame oil, sunflower oil, canola oil, and corn oil. And yeah, I think, I use these 5 oils because they are used a lot in our societies. So it was, it was important. And as you can see from the image, we can see that at the top, the very clear liquid, that's actually the biodiesel that we then purify and have to process. And the part under is the glycerine or glycerol. It's denser, so it will fall to the bottom. And that's actually how we can separate the 2 products, the glycerol and the biodiesel. So, discussion of the results. So, we can see from the graph that sunflower oil, olive oil, and sesame oil were the best. It's hard to tell which one is the best because of the standard deviations, but we can say that all 3 relatively were very good at producing biodiesels. So you might be wondering why it's negative. So it's basically energy released from a system, so the system loses energy. So that's why it's negative. So the bigger the negative number, the better, the more energy is released, and therefore the better the fuel. But then we can see that canola oil systematically produced a biodiesel that was, that released less energy. This may be because of the purity of the oil I used, because usually it's quite suitable for biodiesel synthesis, but in this case, it didn't work well in my research. And the last oil I did, corn oil, despite the multiple attempts producing it, it did not work well. I did not manage to synthesize it. This could show that it's maybe not suitable for biodiesel synthesis. And even though there's some oils that might be better and some that are much worse, we can still use the oils that don't kind of produce biodiesels. We can use those in, for example, fertilizers. And so there's really, we can do a lot with the food waste, and even sugars we can make into bioethanol. So there's really a broad spectrum of things we can do from food waste. So the second part of my research was conducted at the University of Luxembourg. Fortunately enough, I had an internship there and worked in the PhD laboratories of the University of Luxembourg. And I was also fortunate enough to use a differential scanning calorimeter, which is an amazing machine that kind of measures the combustion enthalpy in a very accurate way, something that I did not have in my high school where I did the first part of my research. And so here I looked at something different. I went to 5 local restaurants in Luxembourg, different cuisines and kind of diverse restaurants, and collected their recycled oils. So they use oils such as sunflower oil or peanut oil to fry things such as French fries or chicken or whatever. And I used this oil to make biodiesel. And the process is the same, except that it has to be filtered first because of all the impurities in the frying. And I have to say that most restaurants in Luxembourg have frying machines that reoxidize the oil. So this is extremely helpful in biodiesel synthesis because the oil stays pure and isn't, it's great for biodiesel synthesis. And this was the lab where I made the biodiesel. So discussion of the results. So the graphs we can see here on the right are the graphs produced by the differential scanning calorimeter. So essentially what the machine does is there's intervals of 10 degrees. It increases by intervals of 10 degrees until it reaches 600 degrees. And each time it's measuring the amount of energy released by the biodiesels. So and essentially the integral of this curve will give us the combustion enthalpy. And we can see the different combustion enthalpies in this graph. I only did one trial of this because the machine is quite expensive and it takes around 2 hours to measure each trial. So I did not do multiple trials, but we can kind of get an idea of what the combustion enthalpies are. So yes, so the recycled sunflower oil biodiesels were extremely effective, and even sometimes more effective than they were a tiny bit more effective than the pure oils. And again, as I said, the restaurants reoxidize the oil. It's part of the machine, the frying machine, so it's really effective, and it really helps with biodiesel synthesis. And other oils, such as recycled peanut oil, did not work as well, but it's still very, very effective. And then there's also linseed oil. So yeah, there's a broad spectrum of oils, and essentially they all work well except for the corn oil at the beginning. And this is my works cited. And I would like to conclude this with a small statement. So I really think biodiesels are important, and because we produce a lot of waste, usually all this waste goes to landfills, and we burn it anyways, so why not use it as a fuel where we will ultimately also emit CO2. But yeah, I really think it's important to have a circular economy where everything we use goes back into, gets reused. Thank you so much.
Thank you, David. Today is Friday, right? So yesterday was Thursday. And Thursday literally, you don't know where I'm going here, but Thursday literally means the day of Thor. And Thor is this famous god from the Viking mythology. Well, it turns out, now you see where I'm going. Now, it turns out Thor gave rise to an element, the element thorium. And thorium is the favorite element of Alina Litka. Alina, please come to the stage. Alina is going to tell you a lot of things about another technology that does not produce any CO2, as far as I know. Alina, the floor is yours. Oh, you don't need
this. Sorry. Thank you, Guillaume, for the introduction. So I did my project on nuclear energy, but more specifically, converting uranium power plants to thorium-fueled ones instead. So I came across this topic while just doing individual research, and it just really fascinated me, and I wrote up a report, submitted it to the Jungfrische, and thanks to Guillaume and Susanna, I'm here speaking to all of you, so thank you. A few days ago, here at COP, they actually signed a pledge to triple nuclear by 2050. And personally, I'm very pleased to hear that there's an increasing awareness of nuclear energy at these events. However, coming from Luxembourg, there is a very critical opinion, and they're very against nuclear. So I aim predominantly to provide alternative solutions to the worries of traditional uranium power plants. So just a bit of background information. Nuclear energy is produced on the basis of nuclear fission. So what this is it's just the splitting of an atomic nuclei into two or more smaller nuclei, and this releases substantial amounts of energy. And so this energy predominantly comes from the energy needed to hold the atom together. So this is known as the nuclear force. And in traditional power plants, they make use of the isotope uranium-235 to undergo these nuclear fission reactions. However, the most naturally occurring isotope is uranium-238. So when a neutron collides with a uranium-235 atom, it becomes uranium-236, which is highly unstable, and as a result, it decays very quickly. And normally, the byproducts of this decay would be 2 or 3 neutrons, krypton, barium, iodine, and of course, lots of energy. And the neutrons that are created as a byproduct of this fission reaction then go on to collide with other uranium-235 atoms, and this causes what's known as a nuclear chain reaction. So essentially, these neutrons keep being produced and they keep on colliding with uranium atoms. And so it's a continuous process. So it can be very dangerous if it's not controlled. But the way these neutrons are controlled is through control rods. So an example of this would be boron-10 or cadmium-113. And they basically absorb neutrons so that there are less neutrons flying around the reactor vessel. The reason why these specific isotopes are useful is because they have a high cross-sectional area, meaning that the area by which interactions can take place with the nucleus is greater, so they're more likely to absorb neutrons. And in the bottom images, you can just see an example of nuclear chain reactions and how they're continuous. So the most common nuclear power plant type is a pressurized light water reactor. And so they make use of regular H2O as a moderator and a coolant. So a moderator essentially slows down neutrons. So when a neutron is produced from the fission reaction, it is released with extremely high energy, and so they travel at really high speeds. And when they're traveling at such high speeds, it's very unlikely for them to collide with a uranium atom. And so these neutrons are slowed down by colliding inelastically with the H2O molecules in the moderator, slowing them down to the right speed for the fission reactions to take place. And the water is also acts as a coolant. So what this means is when significant amounts of energy is released from the fission reaction, it heats up the water within the reactor vessel, and this water is known as the coolant. And then the coolant is brought to a different cycle, and the heat is transferred to outside the cycle, where the water can be made into steam, and the steam then spins a turbine, and the turbine generates the electricity, and then the steam is condensed and reused within that cycle. So there's also what's known as heavy water, which is just D2O, so deuterium rather than hydrogen, just the regular hydrogen one. So there's just an image of how a pressurized water reactor works. So you can see there are two different cycles. There's one where the water is in contact with the nuclear fuel, and there's a cycle where the water isn't in contact. So these two different cycles imply that there's no cross-contamination, so the water that's becomes steam is not contaminated because it's not in direct contact with the water that's in the reactor vessel. So actually Cattenom, which isn't too far from Luxembourg, the border of Luxembourg, they have 4 pressurized water reactors, and so the water within the core is held under extreme pressures so that it doesn't actually evaporate or boil to become steam. So that requires a large investment because there's a lot of pressure that needs to be put into this vessel. Here at COP, there's been a lot of talk about small modular reactors as well. And so these require a very low initial capital investment because they're obviously much smaller. And another advantage of small modular reactors is that they are prefabricated in a factory, and they can be transported and installed on-site rather than the large traditional pressurized water reactors, which are often custom designed for a specific location. And so licensing is a lot more harder as well. So what exactly is thorium? It's a radioactive metal, a solid at room temperature, with an atomic number of 90 and an atomic mass of 232. One of the key differences between thorium and uranium is that thorium is fertile and uranium is fissile. So fissile means that it can undergo nuclear fission reactions by itself, whereas thorium is fertile, so it cannot undergo these nuclear fission reactions by itself. And for it to undergo any fission reaction, it needs to be in contact with what's known as a driver material. So this could be plutonium or uranium, for example. So when it's in contact with these fissile materials, then it can undergo its own nuclear fission reaction. So obviously there are advantages and disadvantages. One of the key advantages is that thorium-232 is the only naturally occurring isotope, and so it doesn't need to be enriched, whereas uranium has 3 different isotopes 238, 235, and 234, and only 235 can undergo fissile reactions, and so this needs to be enriched. So when uranium ore is initially mined, only 0.7% of it is actually useful, and so it needs to be enriched to roughly 3 to 5% for it to be useful in a nuclear power plant. Another advantage is that thorium ore is much more naturally abundant than uranium, roughly 3 times. As I mentioned previously, it's also fertile, so it's much safer. So if, for example, something were to go wrong, then you could easily drain the driver material from the thorium and the fission reaction would end immediately. And so it's much more easier to, stop the chain reactions from occurring. And then another advantage is that thorium can be paired with plutonium and basically reuse the plutonium from other traditional power plants. One last advantage is that thorium fission reactions give rise to less transuranic elements. So what this means is so transuranic means elements that are less than 92. So these are elements that are much less radioactive than the byproducts of the uranium reaction. Obviously, there are some disadvantages. The first being that there's an immense lack of research and development, and there's also a low incentive to increase the investment in the thorium-based cycle to make it economically viable. And also, there would also have to be further investments in the driver material, so this would be like the plutonium. So one of the main reactors that thorium can be implemented in is pressurized water reactors. And so there's a large focus on being able to reuse plutonium from previous uranium power plants and reuse that as a driver fuel to initiate the thorium fission reactions. And so this is known as a net zero production because it's being reused. And there are 3 main ways that they can be implemented into existing power plants. The first is a thorium additive. So basically, it's essentially doping the uranium fuel to like 5 or 10% thorium. And this basically improves the fuel performance and generates more energy. And this is mainly just to gain a better feel for how thorium works and just gain more experience. And then there's a thorium MOX, which is a mixed oxide fuel with plutonium. And this is basically a supplement to the uranium cycle where they reuse the plutonium produced from other power plants. And then the last one is a thorium uranium 233 thorium uranium cycle. And this would be a complete replacement of the uranium cycle. However, there needs further research into transport, storage, and safety. So there's this company called Thor Energy based in Norway, and they are focusing on these 3 methods that I've mentioned, and their fuel design are compatible with 90% of reactors around the world, and 90% of which are light water reactors, and they're making use of these previous 3 methods that I mentioned. They've started with the thorium additive in 2018, and they plan on continuing with the thorium mixed oxide fuel, and then from there, the thorium uranium cycle. So in conclusion, thorium is a very innovative method of producing energy. However, the technology and knowledge of thorium fuel is still very immature and will need further development and investments before it can be seen on the market commercially. Hopefully, in the Nuclear Energy Summit in Brussels next March, they'll address the potential future of thorium. Thank you.
So we've heard about different chemical elements so far: carbon, thorium. Now it's time for sulfur. This is your favorite element, right? Please, let's welcome to the stage Ilona Dos. Round of applause, ladies and gentlemen. So Ilona is 20 years old. She just turned 20. She's studying at the University of Leiden. She's passionate with climate issues, but now she's going to present her a problem with the atmosphere, which is not directly related to climate, but to air pollution in our homeland, Luxembourg. Ilona?
Thank you. So 2 years ago, I conducted research on sulfur dioxide and its effects on fructose lichens in Luxembourg. This was from 2021 to 2022 when I was studying at the ISL. And it was to investigate the effect of sulfur dioxide on fructose lichens in Luxembourg. So first of all, what are fructose lichens? So fructose just means, it's a difficult word, but all it means is that it's very intricate and it's very sensitive to air pollution. Next, it's a composite organism, which means that it's a symbiotic relationship with algae and a mushroom. So symbiotic just means that they work together to photosynthesize. And most importantly, they are a bioindicator. So what does bioindicator mean? A bioindicator just means that the specific species can be used to assess the quality of an environment, and this can be done anywhere. And lichen is not the only species that is a bioindicator. So this helped me to find my research question. Since I'm an environmental science major, I wanted to see how this bioindicator is affected by certain emissions. And specifically in the case of lichens, they're very affected by sulfur dioxide, which is produced by roads, by industry. Many industries emit sulfur dioxide, and this has an effect on surrounding ecosystems. And in order to investigate this, I decided to choose 2 sites at different distances from a factory, taking into account wind direction, because obviously wind is going to affect the way in which the sulfur dioxide is moving, and the species, and the height and the abundance, because the bigger the lichen grows and the higher it is, the better the health of the lichen is, and hence the health of the ecosystem is better. So in the end, my research question ended up being, to what extent has sulfur dioxide, as a consequence of the development of a factory complex, affected abundance, height, diameter of fructose lichens, Evernia prunastri and Clonia ciliata? And then for my hypothesis, I hypothesized that as distance from a factory increases, the abundance, the height, and the diameter of fructose lichens will improve, and this would mean that sulfur dioxide levels in soil and in the air decrease. And for me, this was a very, very important research, because we need to, especially in the COP28, we need to be aware of our human impacts. When we create new technologies, even if they are supposedly sustainable, we need to see the end product. What are the consequences of finding new technology? We need to take this into account, especially for ecosystems. And yeah, that industries must make necessary changes, like David said. Biofuels are amazing, and yeah, so yeah, my point was to investigate natural environments. So I took my research in Steinfurt in the Schwarzenhafen, which is a natural reserve. Keep in mind, it's a natural reserve, and yet there's a factory producing sulfur dioxide right next to this fragile ecosystem. And for my methodology, I created a map to show how I conducted my research. So there's the factory. There's 2 sites, so site B and site A. One site is 200 meters away from the factory, and one site is 1 kilometer away. I took into account wind direction. So according to wind directions, the wind would blow towards the west, which would mean that the site A and the site B would be affected by sulfur dioxide. But my hypothesis is that the further away the lichen is from the factory, the less affected they would be. So I conducted a belt transect from this site from site B to site A. A belt transect, it's basically walking along a distance and then doing intervals at each. For me, it was every 200 meters I would take measurements, specifically for abundance, diameter, and the height. So especially for abundance, I would take a quadrat, which we'll see in the next slides. It's a grid. You put it down multiple times, and in ecology studies, if you do this for me, it was 20 trials. You can get a measure for the abundance of lichens. And then the diameter and the height, which was just measured with a ruler. At each distance, I delimited a area of 5 by 5 meters using tape measure, which was my area of study. I put down these quadrats using a random numbers table, and so I recorded the height and the diameter at the 4 corners of the quadrat, and also took into account abiotic factors. So, for example, temperature, humidity, again, wind direction, pH, light exposure, altitude. Like, you can see that there's so many factors that I either can't take into account or that I can measure and see how this would affect my study. But these are so important in ecology studies to take into account, because it's not like you're in a lab. You can't control everything in this study. So yeah, that's important to take into account. So especially for temperature and pH, I was able to record numbers using probes, just sticking it into the ground or taking the soil back into the lab. And this helped me see how my results came to be. Yeah, so my variables were, so the dependent variable, which is basically the variable that's being affected by something. My independent variable are the distances. So the distances, in this case, hypothetically would affect the percentage cover per quadrat. And then the control variables, which would be the location, time of year, number of trials, size of quadrat. These are the things that I can control in my study, and that I can say for sure, yes, like these were taken into account, these were controlled. And then the uncontrolled variables, which I can't control, were especially like climate and human activity. I did my measurements in summer, but the conditions change throughout the year. Again, it's not like being in a lab. So yeah. And then here I drew these myself just to show how big the area is. So the 5 by 5 meters is the area in one 200 meter interval. The tiny gray square, which is 0.5 meters, is the quadrat. If I do this 20 times, I cover around 25% of the zone. So of course there are limitations and errors that I could have made. And then also the square on the right shows how I measured and counted the lichens in a hypothetical quadrat. Small errors are not counted because they're not representative, and in this case it would be around 15 out of 25. This gives you a percentage, and then you do a average, and this gives you average percentage cover for a distance. So then here's some pictures that I took at the site. This is how I took measurements for height and diameter. So diameter on the left and height on the right. More pictures. And then in the end, I got my results. Again, similarly to David, I also have error bars, which show the distribution and the distribution of my findings. So this first graph shows the relationship between the distance from the factory and the average percentage cover of my 2 lichens. Yeah, so this was for a percentage cover. As you can see, there's an upward trend. So on the far right, the distance from the factory is 1 kilometer, and then on the far left, it's 200 meters. So this shows that the further away we're moving from the factory, lichens are able to grow better. And this is because lichens have chlorophyll in them. When they take in sulfur dioxide, this damages the chlorophyll, and they're not able to photosynthesize as well. And this again, this is why we use sulfur dioxide, because it has an effect on the lichen, which is representative of the health of the ecosystem surrounding it. And then, so this is again for the average diameter, but all of them have an upwards trend. But even if this is the case, it doesn't mean that there's a correlation whatsoever. First, I have to do statistical treatments. For this, I did a Spearman's rank. So a Spearman's rank it measures the strength of a correlation. And so I set up a null and alternate hypothesis. And if you've taken a statistics class, you know that the null hypothesis is stating that there's no correlation between my two variables, which I have multiple variables, but it would be, for example, distance from the factory and percentage cover. And then the alternate hypothesis states that there is a statistically significant relationship. And then I also did significance using critical values, which I'll explain later. And then, so yeah, I used the equation on the right to get my numbers. And in the end, this showed a very strong positive correlation between all my variables. So the RS value, which is the coefficient of correlation, for percentage cover distance from the factory was 0.95, 0.98, and 0.95. So we need to know that 1 is the strongest correlation possible. So there's very, very strong positive correlation between percentage cover and distance, average height and distance, and average diameter. And then I wanted to analyze my findings, because as we know, in ecology studies, sometimes things don't go to plan. They're uncontrolled variables that we need to take into account and be able to analyze, which is why we make these graphs. So for the analysis of my findings, overall there's an increase in 35.3% for the percentage cover, 3.7 centimeters for height, and 5.5 centimeters for diameter. We see that when we go back on the graphs, at this distance, at 400 meters, it begins to go down and then back up very quickly. And I wanted to figure out why that was, because obviously there are other factors other than sulfur dioxide. And for the analysis, I did my research. I went back to the site also. I went back to the site at least 5 times to see what was happening really. And at distance 400 meters, I could see mud, a lot of humidity, very waterlogged, and doing more research, you find out that lichens can't really grow in very humid areas. So potentially there's only abiotic factors causing this. And it was really interesting. It was really interesting because, at least for me, it was interesting because for my study, again, I saw this mud, water, and I did my research, and at least what I found is that usually lichen grows better with a lot of water, all these factors that I found on my study that were unsuitable. So, I tried to see maybe there's some sort of thing in mud that makes lichens grow unwell, and I saw that there was clay which could affect how well the lichen was growing, but it's why this study is quite interesting, because I found data that doesn't fit what I saw on the internet. Again, I went back on my graphs, and as we can see, there's also a very strong increase at 700 meters to the 800 meter mark. Again, you go back to your house and you do some research, and I found that at the 800 meter distance, there was a jump in percentage cover, and that could have been because, okay, maybe there's more pollution, but what I found to be most suitable is probably because there was less light. There was also a jump in altitude, which was strange because on my phone it said that there's a jump in altitude, but then on the website there was no change in altitude. So yeah, just taking into account abiotic factors, because of course I don't have any sort of technical, at least at the time I didn't have any technology to measure actual sulfur dioxide concentrations. But in ecology studies, this is what's done. You take into account abiotic factors, you go out into the field, and that makes the study like viable. And then lastly, I looked at the error bars. And the larger the error bar, the higher the cluster growth is. So we need to know that if lichens are struggling to grow in a certain area, they will cluster together because they will all fight for different types of nutrients. So the higher the cluster, the more competition there is for nutrients. Yeah. So as for my evaluation, I really, because of all these factors I keep talking about, I wanted to really evaluate how viable my findings were. So I wrote a bit about that, talked about how there are a lot of varying conditions in my study, possible changes in altitude, which changes how well lichen is able to grow. The way that I maybe set up the quadrat could have been unviable because there's rocks, it's not necessarily straight. And that I only investigated one type of lichen. Basically, the more intricate the structure of a lichen, the more sensitive it is to pollution, which is why I chose it in the first place, because Luxembourgish air pollution, it's not very strong. There's not a lot of air pollution in Luxembourg, so I really wanted to see how the most sensitive organisms are affected, and also that I could have misidentified lichen, which again is to be evaluated. And so in conclusion, really what I wanted to do with this project is to put emphasis on the fact that we need to be aware that like 60% of emissions in the air are caused by large industries. We need to be aware of this, because it's very good to recycle and to do your own part for the environment, but what we need here, the changes that we need are changes towards industries. We need to put certain larger regulations. Especially in my study, it was a industry that was right next to a natural reserve. So we need stronger regulations for industries to be able to avoid this kind of thing from happening. Because obviously, at least from what I saw from my studies, lichen populations were affected by this factory that was only 1 kilometer away. Yeah, thank you.
Thank you, Luna. Our last talk is about milk, among other things. Who had milk this morning for breakfast? Who among you had milk? Okay. Well, maybe after this talk, you may want to talk to Ella and Amelia. Please come to the stage. They will show you a hands-on project to test the quality of milk and other food. Here you go.
Hi, everyone. I'm Amelia, and I'm currently studying at Washington University.
And my name is Ella, and I'm currently studying at Brandeis University, just outside of Boston. So right now, Amelia and I are students at University in America, but when we conducted this experiment, we were high school students at the International School of Luxembourg. And our aim with this project was to take a look at our everyday actions and relate it to something that we find is more important on a global level. And we were kind of really interested in health and climate, and we found that one of the major unknown, or relatively unknown problems that we face today is the problem of mass food adulteration. So we wanted to relate this to our lives in Luxembourg and in Luxembourg as a whole. So we did a small, focused investigation into the presence of food adulteration in our lives in Luxembourg by looking at local milk brands and testing them for popular additives that are often found there. Now, food adulteration is a significant problem. It poses issues for not only our health and public health and safety, but for climate change in general. And it is mostly prevalent in developing countries and areas that are experiencing rapid urbanization, that have unorganized markets and supply chain vulnerability.
So to begin with, what is food adulteration? Food adulteration, or food fraud, as it is colloquially known, is the intentional contamination of food products without the consumer's knowledge, and is often done by producers for economic benefit. At best, it can be misleading to consumers who don't know what they're purchasing, and at worst, it can have serious health effects. Although, like Ella said, it is predominantly common in developing countries, both the US and Europe have had recent cases of food fraud, and an example of this is in 2013 when European countries detected horse meat in frozen foods that were advertised to be beef. So although consumers were obviously outraged at unknowingly consuming horse meat, and there were also concerns over the health and safety of it, as horses are given drugs sometimes which can be harmful to the human health. So although regulations in Luxembourg are very safe, this is an issue across many countries in the world. So food fraud can take many forms, and an example of this is when harmful additives are added to products without consumers' knowledge, and these substances can be either banned or unregulated. So these have harmful effects on consumer health as well as on the environment if they contribute to chemical pollution. Another way food can be contaminated is through the addition of contaminating ingredients, for example, overuse of pesticides, or through medication residues when pharmaceutical drugs are given to animals and are then found in meat or dairy products. Finally, as was given with the horse meat example, the mislabeling of food products, misleading consumers into buying something different than what's advertised, is another form of food fraud.
So the link between adulterated food and the environment and climate change is complex, undeniable, and involves a lot of different interconnected factors. A large part of this is not only the big things that we see in the news that include meats that have been tampered with in the presence of veterinary medications, but a lot of it is due to unsustainable and unregulated agricultural practices. That includes the excessive use of chemical inputs, pesticides, fertilizers, and all of this down the line leads to a loss of biodiversity. It impacts ecosystems and animals, and on top of that, the unregulated industry also results in a lot of improper waste disposal, which just adds to the impact on the environment. These agricultural practices and a lot of rapid urbanization in the world demands monocultural farming, which leads to a lot of deforestation to make space for the farming, and there's a huge loss of biodiversity and a huge excessive water usage, contributing to water scarcity issues that are already prevalent throughout the world. When we're addressing the link between adulterated food and the environment, we have to move towards adopting sustainable and environmentally friendly agricultural practices and regulations, and enhance the strength of our food supply chain.
So as a part of our project, we experimentally looked at the adulteration of milk specifically. We chose this because it is commonly adulterated and was also a simple way to perform chemical tests. So we tested for the presence of 4 adulterants, which were formalin, urea, starch, and pulverized soap. And because of Luxembourg's safe health, food and safety regulations, we didn't expect to find these adulterants in milk. However, we wanted to relate our project in some way to our lives in Luxembourg. So adulteration of milk is prevalent mostly in India, with some reports saying that high percentages of milk, which is sold in India, is adulterated. And all 4 of these adulterants can have serious health effects. For example, urea, when consumed in large quantities, can overburden kidneys, and starch, if consumed by diabetics repeatedly without their knowledge, can have serious health effects, even fatal. So all of our tests were negative, except for urea. However, urea is naturally occurring in dairy products, so is allowed in food and safety regulations.
So essentially, the results of our experiment confirm what we already know. Luxembourg is a highly developed country with the resources and capabilities to place public health and safety at a high priority level and ensure there are strict regulations for the food supply chain industry. Unfortunately, the quality of food distributed on an international and national level globally is not subject to the same regulations and should not and cannot be the responsibility of everyday consumers. We found that there is an at-home DIY solution that we have where we can test our own food and our own products for the presence of additives for food adulteration, but that is not something that's readily available or accessible to everyone worldwide. Governments and corporations are essential, and they need to take steps to prevent the wide-scale food adulteration problem, not only for the health and safety of the public and their citizens, but also for the environment as a scale. And so what would that look like? When we address this problem, it has to be a multifaceted approach. We have to strengthen our regulatory measures. We're investing in monitoring systems that allow for better oversight of the food supply chain. Increase public awareness so people are aware and educated about what they are eating and perhaps can make choices to choose to eat and buy and consume more environmentally friendly food. And in turn with that, we would be promoting sustainable practices and promoting transparency and traceability in our food supply chain. Governments must be collaborating with industry, with NGOs, with other governments in order to collectively address this problem on a worldwide scale, because the problems with food adulteration and especially agricultural practices account for an estimated about 11 to 15% of emissions worldwide. So working together to address this issue is essential when we want to mitigate our effect on climate change. Finally, it's really essential that we invest in research and innovation, that we come up with new technology to help us ensure the strength of our food supply chain and ensure the health and safety of the public, as well as mitigating our effect on climate. Advocating for global cooperation is incredibly important. The food supply chain is multinational, it's all over the world, and it can't just be one country or one corporation or one NGO that works to prevent this. It has to be everyone all at once. And by combining all of these strategies, the regulatory, the educational, technological, and collaborative efforts, it's possible to mitigate the impact of mass food adulteration, both on human health and on the environment, and promote sustainable and resilient food systems. Thank you.
Vielmals merci, Jiderin. So Corinne is left, but I think we have 5 minutes for questions. May I call the young scientist to the stage, please? I know there's one seat missing, but maybe Ella and Amelia, you could stay together. Yeah. Well, you're fit, okay. I will circulate the mic. Is there any first question in the audience? Okay, please share. If there is no first question, we directly turn to the second. Okay, second question. Oh, I actually had a question regarding last. Oh, there's a question. Urea. So you said it naturally occurs in some milk, which makes a lot of sense. But why would you add extra urea in India? Say, does it? Well, why?
A lot of the chemical additives that they add into products like milk are for preservation purposes. So these products will have a longer shelf life and can be sold for longer. That in turn is a result of like economic motives to use food adulteration.
Thank you.
Bartek, related to your project, just wondering whether it's possible actually to implement a sort of device to be able to calculate the amount of CO2. So I understood that you have now the software, so don't you think that a sort of tool can be useful also for the government, so maybe to regulate the amount of CO2? Is that something doable with your actual software?
Yes, so it is possible. So you can combine hardware with software. So you can have like sensors in the roads, for example, stuff like in this sense, and then feed it to some computer on a server somewhere else, and based on this sensor data, for example, from a motorway, calculate the emissions emitted on this road. So this is one of the applications you can make, but of course there are many others, and this is work for many projects in the future. Yeah.
I have a question as well, but maybe a comment to Bartek's presentation and to your question. So always very interested to see where AI is taking us with regard to understanding better how carbon emissions work and all the other greenhouse gases as well. Just as a heads up to you, there's something called Carbon Trace, which is a great organization that is measuring really the main emitter plants throughout the world, and that is basically trying to compile data on how they contribute to the global warming in the specific categories. And there's another project called the Global Carbon Project that just released a report here at COP28 that is also increasing our understanding. And so on the national level, we have Statek, of course, who is doing the inventories of our direct emissions in Luxembourg. And the discussion in Luxembourg is very much also on, okay, we understand direct emissions, so what is going through the chimney, what is being emitted directly, but what about the footprint? What about consumption? And what are patterns to maybe modelize in Luxembourg also on a national scale, how these things really work out? And AI can certainly help us understand better what the consumption levels are in Luxembourg. And that's way more complicated than measuring direct emissions. So there's maybe some future fields of study for you there. Maybe to the two ladies on adulterated milk, my question would be, so in India, that seems to be a very common practice. Is urea the main component, or what are the different types of, how do they adulterate? What is the most standard sort of adulteration practice?
There are many common adulterants of the ones we looked at. We tested for urea, formalin, and starch because they were commonly found. Oftentimes they'll add adulterants like that to improve the visual quality of the milk or to improve the quality when it's tested. And it doesn't actually improve the quality, but it increases the quality that it's given through testing of the milk before it's sold.
Thank you.
I have two remarks or two questions. The first one is about biodiesel, because it's also one matters that I was interested and I am still interested in. You were talking about that you made some testing about different oils and different fats. Is this the results of this testing? Could this be interesting for companies which collect fats and well, used fats, of course, and used oils in Luxembourg, because I know that we already do this, we collect this, and I'm not quite sure, because I'm not an expert, if this is treated in Luxembourg or if this is treated abroad, but this is already done. And I have another question about this lichens that you were talking about after in Steinfurt. Are there any indicators for people who are not experts like me on trees or on other plants, I would say, in Luxembourg, to see if sulfur dioxide is still an issue in Luxembourg? Because I'm somewhat older, and this was an issue in the 80s, and we had what we called at that time saure Regen. This was the sour rain, and this made all the forests die, and I remember it was the spruce trees which really died a lot. So my question is this still an issue today?
Could you smell the sulfur in in Steinfurt? Will we start there?
Well, yeah, sulfur dioxide smells like rotten eggs. So, I mean, I don't think anyone can really smell it. Maybe if you get very close to a factory that's like emitting something. About your question, I'm not sure I know about other bioindicators. I know they exist, but I know it's not about bioindication, but for species, like, I think, I'm not sure which country this was in, but there was also this problem with soot, and like everything became like black because of like the pollution, and animals start adapting because of this. So in polluted areas, for example, if there's white moths, sometimes they will like evolve to become black to hide from predators. So I don't know about bioindication, but for other bioindicators, but I know for species, in very polluted areas, this happens where species start changing in color to adapt. So, yeah. And it was in the UK.
Hello. Yes. So, yeah. So the values I found, in terms of combustion enthalpy, they're helpful because we can see what oils will potentially give us the best biodiesels, and I was actually I chose to pursue this project or this research because online, when I was trying to search for research papers on this, I didn't really find specific research on specific types of oils. I maybe saw generally how much energy is released by biodiesels, but not per oil. And the person I was working with at the University of Luxembourg also told me that he did not find anything on that. So that's why I decided to pursue that. Yeah, and in Luxembourg, most of the food waste in Luxembourg actually goes to Germany and is used there. Sometimes biodiesel, sometimes fertilizer, but around the world or even in Europe, it's still not kind of it's still not done completely, and most of it goes to landfills, especially, I mean, in India, basically all of it goes to landfills and it gets burned, so it's used for nothing. But in Luxembourg there is in Europe it's kind of developing, but it's still not at a point where we're producing enough to sustain the economy, and so we still need diesel for now, but we can work on that.
Corinne allowed us one final question. So, is there any question in the audience? So I got one for Alina. So you said that with a thorium, say, based nuclear economy, we would have less transuranium byproducts. Could you elaborate on that?
Yeah, so like when uranium undergoes fission reactions, a lot of the byproducts is plutonium, which I mentioned in my presentation, could then be reused with like thorium, with a thorium cycle. But when thorium undergoes a fission reaction, because it's already a transuranic element, so its atomic number is 90 rather than uranium, which has 92. So when it undergoes fission reactions, it gives rise to byproducts which are less reactive than the byproducts of a uranium fission reaction. So plutonium wouldn't be generated, and I think that's a very key aspect of thorium, because I think one of the main worries that people have with nuclear energy is obviously nuclear proliferation with the plutonium that's produced. So by avoiding this production of plutonium, and by also reusing the plutonium for something that's better, then I think the thorium cycle is much more just nicer, and there produces less worries for population that might have a nuclear energy power plant nearby.
All right. Well, dear young scientists, many thanks again for your presentation. A round of applause for the youngsters. Thanks so much. Maybe we'll have a group picture. Maybe we have a group picture.